Hello everyone, my name is Piyush Gupta and today I will be talking to you about Kubernetes 101. A quick introduction about me. I work as a senior developer advocate with DigitalOcean. In my previous avatar, I have worked as a developer where I created platforms based on cloud native technologies and also helped customers move their workloads from legacy infrastructure to cloud based infrastructure. I am an active contributor to Kubernetes SIG Contribex project, that's short for contributor experience. You can find me on Kubernetes Slack. My handle there is Pensu91. You can also find me on Twitter with the same handle, that's Pensu91. Or if you are the kind of person who would rather write down an email, please feel free to shoot one at pgupta@digitalocean.com. So this is the agenda for today. Since this is a 101 session, we will be talking about basics of Kubernetes and basics of containers, what made Kubernetes come into the picture. We'll talking about Kubernetes components and what are the objects that you can use when you want to deploy your application on Kubernetes and what are all the workloads. And by the end, we would have a Q&A session as well. So let's get started. Now, one of the basic things that we did when we started with computer science, we had a traditional deployment model where we had an hardware, we had an operating system of top of that, and we had used to run application on top of operating system. Now, in this setup, there was either very little or no isolation between the applications, right? All the applications are running on the same operating system and they had to be very careful about the resource uses, right? So that they don't step on each other's resources. And the way hardware technology grew, we started putting more and more computing power in the hardware. This particular model wasn't more efficient, right? We needed a better way where we can use those computing power in the hardware, in a much efficient way. Hence, virtualization was born, right? And the idea behind virtualization was, if you see on your screens, you have an hardware, you have an operating system. Now, before running your application, you have one more layer, and that's called hypervisor. Hypervisor is essentially a driver like your KVM, and what it does is it helps to provide isolation for multiple application environment. Now, when I say application environment, I basically mean your virtual machines. So, if you look at the diagram, there are two virtual machines running on top of hypervisor, and when you run an application inside any of these virtual machines, those applications would feel like they are running inside a bare metal server. That way, you can share resources of the server and you can provide isolated environment to applications. And this basically provided an easier and efficient way of managing resources. Then what's next? How do you take a leap from there? And that's where containerization come into the picture. Now, if you remember from the last slide, we had two operating systems. One that is running on the hardware and another one that is running inside virtual machine. What if you can remove that redundant operating system layer? Right? Since you already have an operating system, why not make use of that? And that's what container runtime does. Container runtime helps you isolate on operating system level, right? Rather than doing it on, at a kernel level. Now, if you look at the diagram, you have an application, and container runtime would provide you an isolated environment where that application would feel like it's running just on a bare metal hardware. This way, the complexity is further reduced, right? This is the journey so far, right? This is how we have grown. We started with the traditional model where we just had the hardware and the operating system and applications running on top of it. Then we moved on to the virtualization environment where we had the hypervisor coming in and it provided us isolation with separate operating systems. And then we had the container. container runtime coming in that provided virtualization or isolation for specific applications, right? Now, it's not just that the way of doing infrastructure has changed with containerization coming into the picture. The way or the way you design your application has also changed, right? If you look at the diagram on the left side, you have got a traditional way of doing application, right? And that's called a monolith, right? A monolith is an application that contains all the components in it together, right? It gets, let's say your application has a front end and a back end and a database. When you are doing application in a monolithic way, you would combine all of them together and run inside one virtual machine. But when you talk about containerizations, right, when you talk about running containers, you would be breaking that monolith into smaller components. And it's not just the components are not just going to be front end, back end, and database, right? They could be, you can also divide your front end into multiple parts, right? You can divide your login service as separate, and then your if you are running an e-commerce kind of a setup, your cart service would be separate, and then your checkout service would be separate, right? So that way you divide your big monolith into small parts, right? And all these parts are called microservices. So other than just changing the way you deploy your application with advent of containers, you also change the way you design your applications, right? Now, just to give you a definition, what exactly are containers, right? Containers is just a package of application code and all its depending binaries, right? Now, all of its dependencies, right? Now, if you compare it with the virtualization environment, there you had a virtual machine that had its own kernel, it would have its own operating system, and then it would have all the dependencies, and it would have the application code. But in containerized environment, you don't need to worry about the kernel and the operating system, because that all is taken care by the container runtime. You only need to worry about your application code and its dependencies, and that's why containers are pretty small in size, right? If you look at virtual machine size, it can vary from hundreds of MBs, let's say 600 MB, 700 MBs to few GBs, like 1 GB or 2 GB or 3 GB kind of a thing. But when you look at container images, they are pretty small, right? They are like 100 MBs or 200 MBs, right? And containers are basically built using two main kernel features. One is namespace and another is cgroups. Namespaces are the concept that basically provide isolation to your process, right? So in the end of the day, a container is just a process, right? And as we discussed, whenever you run an application, it feels like that it's running directly on the bare metal, right? It doesn't know that there are other processes or other applications running on the same system, and namespaces provide that isolation, right? And cgroups help to control how much resources that particular application or process can use, right? You wouldn't want one application to use all of your RAM or all of your CPUs, right? Right. So cgroups help you limit the resource uses on your container, on your process, or on your application, right? Now, why containers are important, right? What is the value add that they are providing? And one of the things that we just discussed, containers are pretty small in size, so they are resource efficient, right? They don't take too much of disk space, or they don't need too much of processing power to run, and they are pretty fast. When you are booting a virtual machine, you have to boot a kernel, you have to boot a operating system, and it takes some time. But with containers, you can just boot them up within few seconds. And one of the big problem that containers solve is being portable. Like what benefit it provides is, I'm sure if you are working in an organization, you would have overheard this conversation, or probably you would have been part of when different teams are saying that this particular piece of feature was working in my environment. I don't know why it is not working in your environment. Containers solve that problem by creating a portable environment, right? Rather than now, rather than saying that, or rather than running your code in different environment, you can just ship your environment, and it's going to be like 100 MB or 200 MB, so it's not going to take too much toll to ship that as well, right? Just few more concepts about containers and some terminology that we need to get familiar with, right? So container images are basically images that contain your application code and your dependencies, right? Containers are the running instance of that images, right? Container runtime here is the driver that makes running containers possible on your environment or on your host, right? And I guess when containerization and the microservices started, Docker was the only container runtime, or at least the only popular container runtime, right? But right now you have a lot of options that you can choose from. It could be the containerd, or it could be CRI-O, or it could be Kata containers, right? And these different projects solve the containerization problem in different ways. You can choose any one of them based on your preferences, and then you need a place to store all the container images, right? And that's where container registries come into the picture, right? Where you can store those images, you can push them, you can pull them, right? And you can do all sort of operations there. Moving on. Now, containers are all well and good, right? But if you remember, we discussed about breaking a monolith into microservices, and we discussed that when you break down a monolith, there could be multiple microservices, right? And if you have a big application, or if you have an, let's say, a high availability kind of a setup, you can end up running hundreds of microservices, and each microservice would run inside one container. In that case, you end up having hundreds of containers, right? Now, the problem there is, how would you manage them, right? How would you know if something goes wrong? How would you know which container has the problem? How do you scale them, right? How do you restart them, right? And those become practical problem at that scale, right? If you are running, let's say, 5 containers, 10 containers, not a problem. But when you are running hundreds of containers, right, it eventually becomes a problem. And that's the problem that container orchestration systems are trying to solve. They handle the deployment of your applications, they handle the management, they do health checks, right? Just to make sure that containers are up and running. They run security checks, they make sure that your networking policies are enforced, among other things, and much more, right? And one of the most famous container orchestration system is Kubernetes, right? It's also known as KATS, right? Because there are 8 letters between K and S, right? And it came out of Borg. Borg is Google's internal container cluster. Google has been running containers in their production environment for quite some time, and when containerization started to pick up pace, they open sourced their internal engine, and they named it Kubernetes, right? And the way Kubernetes has grown is phenomenal. It is one of the most famous open source project on GitHub, right? And it's highly developed as well, right? There are thousands of developers fixing bugs, right? Creating new features, and there are features that keep moving from alpha to beta to stable, right? And they have, I guess, 4 release in a year, around 1 release per quarter. So there's a lot of involvement happening in Kubernetes, and it's evolving pretty rapidly, right? And Kubernetes is governed by CNCF, that's short for Cloud Native Computing Foundation, and they basically oversee that Kubernetes governance is done in an unbiased way, and all the community code of conduct and everything is followed. Now, let's talk about why Kubernetes. And most of the points here would be similar to why would you want to use containers, right? The only difference is Kubernetes also creates a layer on top of using containers, right? So, let's get into it. Kubernetes is resource efficient, right? And it again comes back from the containers. Since containers are small in size, they are pretty fast, right? And they don't require much computing power to run. They are very resource efficient, and hence Kubernetes is also pretty resource efficient. It has a scheduler that makes sure that your container would run on a node that is not heavily loaded already, so that your applications get enough resources to run successfully, right? uh, it increases productivity since containers are pretty fast. They can boot up pretty quickly, and you can run your workloads, you can test your workloads, you can test out the new features that you have been coding. And it also increases the CI/CD pipelines, right? When you are doing CI/CD, you will have to create new environments and destroy them, and that happens pretty frequently. Now, if you look at the virtual machine based environment, every machine is gonna take few minutes to boot up, right? While containers can do that in second. So your speed of CI/CD pipelines drastically improves. Kubernetes provides scalability. You can just run one command, and that one command can scale up your application or scale down your application, right? So you don't need to worry about how is that going to happen, because Kubernetes takes care of that internally. And then you have high availability concept as well. Kubernetes has an inbuilt concept called services. We will talk about that in a bit. And services can help you maintain high availability. Uh, it basically means when you have multiple copies of your application running, Kubernetes can automatically load balance your request across those multiple copies. And if one of the copy goes down due to any reason, it will automatically remove that from one of its endpoints, and your users won't feel any downtime. And it also has self-healing capacity. Kubernetes always makes sure to maintain the state, right? And what I mean by that is, when you say that I need 3 copies of my application running, Kubernetes always makes sure that you have 3 copies of your application running. If due to any reason one of the copies goes down, let's say you have a node going down, right? Kubernetes will make sure that one copy in its place comes up again. It automatically does that, right? This is a simple component diagram for Kubernetes, right? It is in no way means to be an exhaustive list of components, right? Since this is a 101 session, we are not diving deep much into the architecture, but just to give you an overview, we'll start from the nodes, right? So Kubernetes has a typical master node architecture, right? Where you have a master or a control plane, right? That takes care of all the management actions, right? And then you have a worker plane, and worker plane have nodes, right, who execute the instructions that we give to the control plane, right? So if you look at the diagram, we have got nodes, and these nodes primarily run 2 components. One is called kubelet and one is called kubeproxy, right? That kproxy is short for kubeproxy. Kubelet is the agent that works as a bridge between the worker node and the control plane. Kubelet takes all the information about the node, like CPU, RAM, disk pressure, all those things, and it provides it to the control plane, so that control plane can make an effective decision if a new workload should go on this node or not. Kubeproxy essentially takes care of networking related components, right? When you are running a complicated system such as Kubernetes, networking become a complicated issue to solve. And for that, kubeproxy sets up IP table rules, right? So that your packets can be reached at the right place, right? And then if you look at the control plane, we have API server in the center, and API server is the center for all the Kubernetes components. Every single component in Kubernetes talks to API server, and API server then uh, either notifies the relevant components, or maintains the state, right, in a proper way, so that you have the cluster up and running, right? There is one important component that's called etcd, right? You can call it etcd or etcd depending on whatever you are comfortable with. And etcd basically stores the cluster data or the cluster state, right? If by due to any reason the cluster goes down, and if you have etcd backup with you, you can always bring that cluster up, right? Because all the state is stored in that database. You have then got a scheduler, right? A scheduler is the one who makes decision on where the workload should go, on which node workload should be running on, and it has some of the data points based on which it makes that decision. Something like is the node up, how much resources it has, if we deploy this particular workload on this node, would it be able to run properly, based on requirements, does that node fulfill those requirements, among other things. Then you have got a controller manager. A controller manager is something that makes sure that the state is maintained inside the cluster, right? And there are multiple controller managers. There is usually one controller manager for all for each of the resources that you run inside Kubernetes cluster. And then you have cloud controller manager as well, and that can be used to interact with the cloud providers, right? Cloud controller manager is an optional component if you look at this diagram, but all of the other components, they have to exist in order for a Kubernetes cluster to work properly, right? Let's move on, right? So this slide basically just writes down of all the components that we saw in the last slide. If you remember, we talked about control plane and nodes. These are the two major buckets, and within control plane we have got API server, a scheduler, a cloud and Kubernetes controller, and then etcd database. And on the node we have got two agents running. One is kubelet and one is kubeproxy, right? Now how do you connect to that Kubernetes cluster, right? Now I have not covered about creating a Kubernetes cluster because there could be multiple ways to do that, right? And I will just talk about that a bit. It depending on the provider that you are working with. Let's say either with DigitalOcean or with any other cloud provider, or you are creating a local cluster, right? Either using Minikube or kubeadm or something like that. Depending on that, there could be multiple ways to set up a Kubernetes cluster, right? Once you have set that up, right, how do you interact to it? How do you talk to the Kubernetes cluster, right? And if you remember from the previous slides, right, we discussed that every single component in the Kubernetes cluster talk to the API server. Similarly, we would also be talking to the API server when you want to talk to the Kubernetes cluster, when you want to interact with that cluster, right? And API server, as the name itself suggests, can respond to curl APIs, right? You can use that, or you can use client libraries as well. There are multiple client libraries or multiple client library implementations available. If you want to use a Go based client, or if you want to use a Python based client, right, you can use that. Now this works programmatically, right? You can wrap all these APIs in a script, and you can use them to interact with your Kubernetes cluster. But as an administrator, or as a regular user, you probably wouldn't want to use the APIs, right? For that, Kubernetes has an API wrapper, and that's called kubectl. It depends. There are a lot of people who call it with different names. It could be called kubectl, it could be called kubectl, it could be called kubecontrol, whatever you are comfortable with, right? So now kubectl is basically a command line tool that you can use to interact with the control plane, right? And how it helps is when you make API calls to the API server to achieve one task, you might have to make multiple calls. kubectl abstracts that out, right? It provides you some functionalities like get, create, delete, describe, right? Basically all your CRUD operations you can do. And when you are talking to the API server, at at some points you might have to filter out the results as well, right? You might not want all the information that API server is giving you. kubectl does it automatically for you, right? Now, this was all about Kubernetes architecture, how you interact with it, what are containers, right? Next, we are going to be talking about what are the core objects and workloads in the Kubernetes world, right? So one of the core concept that you need to know about Kubernetes is namespaces, right? Now, don't confuse Kubernetes namespaces with the kernel namespaces. However, the functionality is quite similar, right? Kernel namespaces provide isolation to processes. Kubernetes namespaces provide isolation to Kubernetes resources, right? So namespaces are basically an abstraction that allows you to divide your cluster into multiple virtual clusters, right? Think of it as a way where you can group some resources, right? And restrict them to be in their own environment, right? They don't know what's going on outside that particular environment, right? And if you look at the example, let's say you are running an organization and which has different team, right? You have got, let's say, a dev team, a production team, and a billing team. So what you can do is you can create different namespaces for these team, right? And you can also restrict how much resources they can access, right? So this gives you a way of isolating your Kubernetes resources itself, right? And this is the primary mechanism that is used for scoping and limiting your accesses. And when you start up a Kubernetes cluster, you usually get three namespaces by default. One is the default namespace where you can deploy your workloads, create your resources, right? You have the kube system and the kube public namespaces as well, right? Now pods are the core resource in Kubernetes. Whatever workload you would run, it runs as a pod, right? Pod is the smallest unit of deployment in the Kubernetes world, right? And it can contain more than one containers, right? So just to give you a parity, we have been talking about containers till now, and when you group containers together, what you get is a pod, and pod can also contain one container, right? But from Kubernetes point of view, the logical unit of deployment is pod, right? And it runs as a single unit. So whatever the containers that are there inside that pod would run on one node itself, right? Because Kubernetes won't schedule 50% of the pod on one node and 50% of the pod on another node, right? And all these pods or all the containers inside the pod share the network and storage resources. Now if you look at the diagram, we have four pods running there, right? And one of the pod has only one container, one pod has two, one pod has three containers, and one pod has got five containers, right? So one, two, and three containers, right? Rest two are volumes. But the idea behind or the way you can picture pods is these are a group of containers that are scheduled together. That's it, right? And now, how do you define pod? How do you tell Kubernetes that okay, I want to run a pod, right? Remember that you cannot tell Kubernetes to run a container, right? Kubernetes doesn't understand containers. Kubernetes understands pods. So you usually talk to Kubernetes via kubectl, and the configuration is put up either in form of a YAML file or a JSON file, right? So in this slide I am using a YAML file, right? You have to define the API version, which API group you have been talking to, or you want to post this request to, and then you define a kind. Kind is pod here. You define the name of the pod, and then in this pack section you basically define the containers, right? Here you can tell Kubernetes that okay, this is the container that I want to run, this is the name, and this is the image that will be used to run this particular container. Now in the container section you can have multiple containers, right? That's what we discussed in the last slide. You can run multiple containers inside one pod. So if you have multiple containers, you can just list them here, right? And then you can just deploy that pod using a simple kubectl command, kubectl apply -f pod.yml. This basically posts the request to the API server, and the other relevant components get notified. They take actions accordingly, and you get your pod up, right? Now pod is again a very small individual unit, right? But if you are running, if you are looking to run an application, right, the resource that you usually use is called a deployment, right? Deployment is the object that will contain your application, right? And one of the good things with deployments is you can run multiple replicas, right? So if you look at the YML on the right side of your screen, you will see I'm running three replicas of this deployment, right? And when you say that you want to run three replicas, the onus is now on Kubernetes to make sure that there are three replicas running at any given point of time, right? If one of the replicas fails, due to any reason, Kubernetes will make sure that it creates a new pod, right? So when I say three replicas, it basically means it would be running three pods, right? And you can also scale up and down these pods, right? You can just run a simple kubectl command saying kubectl scale deployment, and then you can provide the deployment name and the number of replicas that you need, and Kubernetes will scale it up. And when you want to scale it down, you can run the same command with the lesser number of replicas, and it will scale it down, right? And if you look at the YML file, you have the app/v1, that's the API group which deployments belong to, right? And then you can say kind deployment, you can put the names, the labels, right? You can set the number of replicas, and again towards the bottom you have the specifications or the spec where you tell that what container you would want to run as part of this deployment. And again, you can do the same thing. If you have multiple containers, you can use them, and you can also expose ports, right? Sometimes your application would work on a specific port and you would want to access that, so you would have to expose it so that you can use that particular port, and you can mention that in your YML file. Right now, when you have created your deployment, right, when you have deployed your application as part of a deployment, you would need to access it, right? And in Kubernetes world, that access process happens via services, right? So what you do is you expose your application or your deployment or your pod via services, and all the other applications talk to that particular application via that service itself, right? Why is it important, right? Think of a scenario where you are running an application, and that application has multiple microservices running, and all these services are talking to each other, let's say via IPs, right? Now the problem is containers can go down, right? And when a container dies down and a new container comes up, Kubernetes will make sure that the new container comes up. When it does, it would have a different IP, Now in that case, all the other components will have to be updated with the new IP, and that becomes a very complicated task to do. So as a solution, what you do is you use an abstraction on top of that, and that abstraction is called services. Services are basically a logical entity that keeps track of a particular deployment. If and they know all the IPs of that deployment. Let's say you are running 5 replicas, they know, services know all the 5 IPs. If any one of the copies or any one of the replica goes down and a new one comes up, services updates its database of those IPs, right? Services can also help you in load balancing traffics, right? As we just discussed, if unhealthy pod goes down, a new healthy one will come up, and services will just update that IP, so that whenever a request is coming for that particular deployment, it always goes to an healthy pod. And this selection happens via labels. So if you remember from the deployment YML, we had set up some labels, and using those labels, services can track which copies are up and which copies are not working, right? If you look at the diagram, users usually indicate with the service, and service load balance that request among replicas across nodes as well, right? And there are basically 3 types of services. We have cluster IP, that's essentially for internal communication. When services just want to talk internally, there might be some services in your application environment whom you don't want to expose to the outer world. For those services, you can use the type as cluster IP. Then you have node port and load balancer. We will just take a look in a moment. Right. So node port is one of the widely used service type, and the way node port works is you tell your application that or basically when you create a service, you expose a particular port on a type node port, right? And when you do that, when you tell the target port or let Kubernetes choose it, that particular port get exposed on all the worker nodes, right? So if you look at the diagram on the screen, you will see I have chosen the node port as 30,333. There is a Flask deployment that is running, and it is exposed via node port on port 30,333. Now, as soon as you create the service, the kube-proxy agent, if you remember from the earlier slides, we had a kube-proxy agent doing IP table rule manipulations, right? So when you expose it as a node port, the kube-proxy agent updates IP table rules on all the nodes, that if any request is coming on this particular port, it would be redirected to my Flask application, right? So you can go to the public IP of any of the node, and on that particular port, you would be able to talk to the that particular service. Another type of service is load balancer, and what load balancer helps you with is it helps you create a cloud provided load balancer, right? If you are running you are running Kubernetes with a cloud provider, and if you expose a service as a load balancer, it will create a cloud provider managed load balancer, depending that there is a driver for it, and then you can use that load balancer to manage communication with your request, right? And of course, we need to talk about storage when we are talking about deployments. Now, containers were designed to be stateless, right? That's what gives them the agility and resource efficiency and all those things. But when you are talking about real life applications or real world applications, right? Those are not stateless, right? You need a way to maintain state. You need a way to store the data. You need to work on that data, analyze it, use it in some other form, right? So to solve that problem, Kubernetes has a concept of PVs, right? PV is short for persistent volume, right? The persistent volume is basically a storage volume that can be attached to the pod, right? And these volumes can either be created by the administrator in advance, that's called static provisioning, or you can create these volumes on the fly, that's called dynamic provisioning, right? Now, how does a pod uses these volumes, right? For that, you have to request that to Kubernetes API server that you would want let's say a 10 GB SSD disk, right? This request part happens via PVC. That's called a persistent volume claim, right? So when you are creating your pod, you basically claim, or you create a PVC a request that I am going to need a 10 GB SSD disk for this pod to run. Now, if you are using static provisioning, and if the volume is already created, it would by your administrator, it would be attached to the pod. If we are using dynamic provisioning, that usually happens via something known as the storage class. So the request will go to the storage class. Storage class will create the concerned volume using the whatever driver it has been configured to use, and attach that volume to the pod. Once that volume is attached, only then the pod will be able to start, right? uh, One more advantage of using volumes is, if you remember, we talked all the containers inside a pod share storage and network resources, right? So when you write something on a volume from one container, you can read it from another container. So it can also be used as a communication tool, right? And the next evolution of the storage drivers is something known as CSI, that's short for Container Storage Interface. So, since storage is a pretty vast area and there are a lot of vendors who do storage their own way, so you can't have one single way of doing things. Hence, Kubernetes community has created a CSI plugin that you can use to deploy in your cluster, and depending on what driver you have deployed, you can request those specific type of volumes, right? Right now, after storage, you would also need to uh, provide some configuration values to your applications, right? Probably some environment variables or some configuration files to get your application up, right? All of these things can be done via config maps. What config maps are? They are basically resources that store configuration data as key value pairs, right? Uh, you may also need to provide some secret information to your application, something like username, passwords, or authentication tokens or SSH keys or something like that. For that, Kubernetes has a secrets resource, right? Now the secret is by default base 64 encoded, right? So I mean, it's not the highest level of security, it's not even encrypted, it's just encoded, but at least it's not visible to the plain eyes. But there are a lot of plugins available that can help you encrypt your secrets, and you should use them when you are running a production environment, because base 64 encoding can always be decoded, right? And you can use the config maps and secrets either as environment variables, or you can mount them as a volume to your pod. Now, just to recap, right, what all we have discussed, right? We talked about pods, right? We talked about namespaces, deployments, services, config map, secrets, persistent volumes, right? And all of these things together, right, make an application, right? Now, if you think from a developer's point of view, or from a package management point of view, packaging all of this together becomes a nightmare, because you have got lot of components, right? And those components needs to be deployed and then configured, and then make sure that they are properly interacting with each other, right? Networking is set up properly, storage classes are set up properly, right? And this becomes a big task to take care of. Hence, we have a package manager for Kubernetes, right? And it's called Helm, right? What Helm does is it helps you, or it helps developers to package, manage, and deploy applications and services to Kubernetes cluster, right? And these packages are basically called Helm charts, right? So if I want to simplify it, Helm charts are basically just configuration files that contain all the application configuration data, right? Starting from the pod YML to the, excuse me, starting from the deployment YML to the service YML to the storage classes to multiple config maps to secrets and everything, right? And the way you talk to this is via a Helm client, right? So Helm client is a binary that gets installed on your workstation, and you can configure it to talk to your Kubernetes cluster, and using that you can install multiple Helm charts, right? And also Helm charts have their own repositories, right? Where they can be versioned as well, right? Whenever you release a new, let's say whenever you release a new software, you version them, right? Release 1.0 and then release 2.0, release 3.0. Same thing can be done with Helm charts as well. Also, they provide you an option of configuration before installing, right? If there is some secret information that you need to provide, you don't need to keep it in the Helm charts, right? You can use environment variables, and then you can provide those configuration values at the time of installing those Helm charts, right? And at the bottom you can see you have to first run Helm init, that creates an Helm environment in your current directory, and then you can just go and install an application, and it's as simple as that, running Helm install stable/WordPress. Here stable is your repository and WordPress is your application, right? So we have talked a lot about basics of Kubernetes, what are all the core components, how you can run your applications, what are all the basic things that you need to remember when you are running your application in the Kubernetes world, right? But there is much more to Kubernetes, right? This doesn't end here, right? There are a lot of advanced topics that you can explore, right? Kubernetes has got auto scaling, right? When you are running your application and you need more copies on the fly, right? You can run them, and you can create multiple copies at the runtime using auto scaling. Kubernetes can have, deeper access management using RBAC, that is short for role based access control. You can have resource quotas for individual pods as well, so that if there is a memory leak or anything like that, that can be prevented, where you can restrict that this particular pod can only consume this many resources, right? And Kubernetes is by design extensible, right? You can virtually extend each and every single component of Kubernetes, right? Starting from kubectl to kubelet to even your API server. You can even run your own API server inside a Kubernetes cluster, right? And of course logging and monitoring as well. Since Kubernetes manages a very complicated environment where there are hundreds or thousands of pods are running, you need logging and monitoring mechanisms to check in case if something fails, where exactly the issue is, or you would want to check logs of your application just to make sure that things are working fine. And all those capabilities come with Kubernetes. Most of these capabilities come with Kubernetes inbuilt. Some of these capabilities can be installed via simple plugin management and much more, right? There are a lot of other things that you can do with Kubernetes, right? So that's all I had. I hope you got to learn something from this session, and if you have any questions or any concerns, I will be I am reachable at Pensu91. That's my Twitter ID. You can reach out to me there, and I would love to talk to you. Thank you for watching.